Alright guys, we're going to be talking about physical thermochemistry today. We're going to go a little bit quicker just because you have watched the kinetic molecular theory notes before this. So, as you can see, we are in our room. So no dogs in this one. So thermochemistry, we're going to be talking a lot about heat, temperature, and energy, basically. So thermochemistry is going to be the relationship between that chemistry and the energy. So it's honestly a combination of physics and chemistry. Any change in physical or chemical is accompanied by a change in energy. So basically, if we're changing what it is, there's also a change in energy or heat. And you can see here, from solid to liquid to gas, we're changing the amount of heat, and we're also changing the state that it's in. So a couple of vocabulary terms. Energy is the capacity for doing work or supplying heat. Work is a term used in physics a lot. Work is a force acting over a distance. It's just force over distance. And heat is that flow of energy. And we talk about heat with temperature, but they're two different things. So if we're going to think about energy, it's going to be a quantity. It is a number. Energy is a number, normally recorded in joules. Heat and work, two different ways that an object can exchange energy with other objects. So there can either be a force or there can be heat or both. Alright, so we can either have kinetic energy or potential energy. These two terms you may have heard before. Kinetic energy, that's going to be our motion energy, our moving energy. Potential energy is our potential energy, meaning like it's sitting still, it's not moving, but it has that potential of energy. That's kind of how I think of it. But it does still contain energy. Kinetic energy, well, if we go down from there, there's thermal energy, and that's going to be associated with temperature and heat. And from potential energy, we go down from there and we see chemical energy, which is associated with our subatomic particles. So next, I see temperature and heat. Temperature is the measure of kinetic energy of particles. Heat is that energy. Heat is energy that transfers. Energy is the key word there. And it's going to transfer from an object that is hot to an object that is cool. So if heat already exists in one thing, it will sit there until something around it is colder, and it will move to that cold place to make that hotter. So basically, when you open up your front door in the summer, the heat is actually moving in, the air conditioning is not going out, which is pretty cool. So we can also see here temperature is that measure of kinetic energy, the moving energy. At low temperature, they're not going as fast, and at higher temperature, they're going much faster. So faster rate, higher temperature. Heat is going to move from an object that is hotter to a lower temperature object, making it warmer in a perceived way. Heat is the amount of heat an object contains is based on temperature, mass, and that phase of that matter. So if the particles are in the liquid phase and they're really hot and there's a bunch of it, we're going to have a lot of heat there. Heat is going to be like that average kinetic. Heat is the total amount of energy, whereas temperature is that average amount of kinetic energy. So heat is that total, so if we have more of those particles and they're moving quickly and they're in that liquid phase, we will have more heat, as opposed to like if we have less of those particles but the same temperature in the same phase, there will be less heat. So question here, which one has the higher temperature, a pot of boiling water or an ice cube, or an iceberg, temperature is that average kinetic energy, so think of it as like the pot of boiling water will have a higher average temperature, but that iceberg will have a lower average temperature. But which one contains more heat? Well, there's more particles in that iceberg than in the pot of boiling water, so the iceberg will actually contain more heat. Next, we move on to some entropy kind of things. So some more vocabulary terms, the system and the surroundings. The system is going to be like the main thing we're focused on, the thing in the middle, and the surroundings is going to be everything around it. Pretty basic. We're going to study the exchange between the system and the surroundings and the heat involved with that. So the law of conservation of energy, much like the law of conservation of mass or the law of conservation of anything, energy cannot be created nor destroyed. The energy is just transferred or converted from between different forms. The total amount of energy, though, stays the exact same throughout the entire process. So now we can talk about heat in reference to that law of the law of conservation of energy. So the first law of thermodynamics says that the total amount of energy, all the kinetic energy and all the potential energy, is constant in the universe. There is no change in energy in the universe, and we say that that is zero. So delta energy of the universe, here is always going to be zero. Delta energy of the universe equals delta energy of the system plus the delta energy of the surroundings. The change in the energy of the system plus the change in energy of the surroundings, because they're just going to flip-flop back and forth. So the addition of these two numbers will always be the exact same, or zero. The change in the energy of the system plus the change in energy of the surroundings equals zero. So if this one loses, this one is going to gain. If that one gains, or that one loses, then that one's going to gain. The change will always equal zero. So the change in energy of the system will always be equal to the negative change in energy of the surroundings. Some more vocabulary terms. Endothermic reactions, the heat flows into the system from the surroundings. So endothermic, the heat flows from the surroundings, from out here, into the system. The system itself is going to gain heat. The system is going to get hotter, but the surroundings get cool. And then there's exothermic, the heat flows out of the system into the surroundings, so the system itself gets cooler and the surroundings heat up. Think of it, so if I give you the example of a hand warmer makes your hands hot. Your hands are the surroundings. The surroundings are heating up. That's going to be an exothermic reaction. Kinetic molecular theory, which we talked about earlier. State of matter depends on two factors, the amount of kinetic energy and the particle strength, the forces of attraction between them. So now we're jumping into a different part of heat, talking about like heat capacity and specific heat, and like the actual mathematics behind heat. So objects absorb heat at different rates. So think of it like when you're boiling water. It's better to use a wooden spoon as opposed to a metal spoon. The wooden spoon will absorb heat slower than the metal spoon. You'll get burned by the metal spoon quicker. So heat capacity is that vocabulary term that we are talking about there. Heat capacity is the quantity of heat required to raise the temperature of the system by 1 degree Celsius. So how much heat, how much energy does it take to raise the temperature of the system, the thing that we're measuring? So specific heat, the amount of heat needed to raise the temperature of 1 gram of an object by 1 degree Celsius. So before we were talking about heat capacity, now we're talking about specific heat. Specific heat has to do with 1 gram of that object by 1 degree Celsius. The lower the specific heat, the more its temperature rises when a given amount of energy is absorbed. So when we have a lower specific heat, our temperature will raise more with energy. So on a hot day, compare the temperature of the pool of water versus the concrete beside it. We all know that the water does not get as hot as the concrete around it. That's why we jump in the pool quickly, so that our feet aren't getting burned on the concrete. So the specific heat of the concrete is lower because it's getting the same amount of energy as the pool. They're both getting the same amount of energy, but the concrete gets hotter, which means its specific heat is actually lower, because it doesn't take as much heat to raise the temperature by a degree Celsius. So here's the mathematical equation behind it. Q equals mc times delta T. Q is that change in heat. It's going to be in joules. M is the mass in grams. C is specific heat in joules per gram degree Celsius. And delta T is going to be your change in temperature, which is just T final minus T initial. Another unit for heat or work is calories. And 1 calorie is going to be equal to 4.184 joules. You do not need to memorize that conversion. I will never ask you to do that in your head. Alright, so let's do some math here. The temperature of a 95.4 gram piece of copper increases from 25 degrees Celsius to 48 degrees Celsius when the metal absorbs 849 joules of heat. What is the specific heat? So, Q equals mc times delta T. Sometimes they put C sub P for specific heat. That's how I know how to say it. So the temperature of a 95.4 gram, so that's the mass, 95.4 of copper increases from 25 to 48. So T final minus T initial gives us delta T. T final is 48 because it increases to 48 minus our initial. It started at 25. Our delta T is delta T is, oh, I didn't calculate it. I just put it in there. So we'll just do that. And then our C sub P is what we're looking for. And Q is actually this 849 joules. So if we do our math, C sub P is going to come out to 0.39 joules per gram degree Celsius. Alright. How much heat is required to raise the temperature of 250 grams of water to 52 degrees Celsius? So for that one, I see the same equation. Oops. So Q equals mc sub P delta T. Q is what we're looking for. M is 250 grams. C sub P, we can look up on our reference table, and for liquid water is 4.18 joules per gram degree Celsius. And it says we're raising the water, so how much heat is required to raise the temperature of 250 grams of water 52 degrees Celsius. So we're raising it by 52 degrees Celsius. That's not our final temperature, that's the actual change in temperature. So I do the math. Q is equal to 54,340 joules. And with sig figs, you just get 54,000. Alright. Moving on. Now we're going to be talking about heating curves. So a heating curve is a graph of the temperature versus the time. We're going to see phase changes in these heating curves, and we're going to see energy changes and heat, basically. It's going to show the physical changes, like the phase changes, and as well as the heat changes and temperature changes. And then primarily we look at the heating curve of water. So the heating curve of water is here. So we see over time, down here, over time, so time's going this way, temperature increase is going up. Over time, as we're just like gradually heating something, we're starting down here at ice, because I see 0 degrees Celsius here. Below 0 degrees Celsius, it is frozen. So this is solid. And here is going to be our phase change. Everything from here to here is our liquid. another phase change at 100 degrees Celsius because that's when water boils. So that's our gas. Same thing. So how much heat is required to convert 55 grams of liquid water at 22 degrees Celsius to steam at 105 degrees Celsius? I'm actually going to skip over this problem because it's just another Q equals mc sub p delta T. If you want help on it, just come find me and we'll work through it together. So moving on, the heating curve can also be reversed to where our temperature is actually decreasing over time. Same exact thing, it's just backwards. So same thing, up here is your solid, here is your liquid, and here's your gas. Or sorry, oh, I did that way backwards. Above 100 degrees Celsius is the gas. Here is your liquid. And here is your solid. Everything that's flatlined is where temperature doesn't change, but the heat changes. The energy changes, but the temperature does not. Those are your phase changes. So you can see here, delta H, that's your entropy. H is entropy. Your delta H of the condensation is equal to the negative delta H of your vaporization. So at that phase change, the condensation energy turns into vaporization energy. It kind of just like flip-flops between those surroundings and system. Same with the solidification and fusion down here. So energy exchange. With the energy exchange, heat and work are just flip-flopping between the system and the surroundings, and you can use the equations there to figure out which way it's going. So here, delta E, E is your energy. Energy is exchanged between the system and the surroundings through heat and work. So we have heat energy and we have work energy. Q is heat, W is work. The change in energy does not depend on how you got there. It just depends on what you started with and how you're finishing. The change in the internal energy of the system only depends on the amount of energy in the system at the beginning and at the end. That's it. Q and W do depend on how you get there. So delta E is going to equal Q plus W. Delta E is the change in the internal energy of a system, energy. Q is the heat flowing into or out of the system. So if it's negative, the energy is leaving the surroundings, leaving to the surroundings. So if it's negative Q, then it's leaving our system and going to the surroundings. If it's a positive Q, the energy is coming from the surroundings into the system. So think of it like if you're the system and you're adding Q, so your Q is positive, then you are gaining heat. W is work done by or on the system. If W is negative, the work is done by the system on the surroundings, so the work is done onto the surroundings. Think of it like if you are working in a field, you're going to be pretty negative if you are working really, really hard for the surroundings. If W is positive, then the work is being done on the system by the surroundings. So think of it like if work is being done on you, like if you're I don't know, at the nail salon or something, or you're at a restaurant, the surroundings are doing work on you so that you can be happy and positive. So if we look here, energy exchange, I see a system, which is the, I guess, liquid underneath that piston. The surroundings would be what's around it. And I see a pressure decrease. Making, so on the left hand side one, the change in energy, there is no work being done, because work has to do with force and distance. There is no force really being applied here, so the change in energy here is just that Q, but when we take out the stops right there, there is a force being applied. But it's being applied, force times distance is work, and the distance kind of has to do with that circular part. So we have to do the distance as the area of that circle times that change in height that's occurring for the work. So if we're looking at work, pressure, and volume, work, we can also use negative P times delta V. So if there's an expansion in our volume, delta V is increasing, we will have negative work, and the energy on the system is going to decrease. Work has been done by the system on the surroundings. If the work is being done by the system, because the volume is increasing, changing that surrounding results. If delta V is decreasing, so our volume is getting smaller, then our work is getting larger, and the energy on the system is going to increase because that force is going to increase. The work is being done on the system by the surroundings because we're pushing down from the surroundings onto the system, making it endothermic. So, here I see the exact same thing as before. The gas in the piston will be warmer since all the energy went into heat. I can also see this as a pressure kind of problem, with the pressure being higher on the left, the temperature raising because the collisions are occurring faster, but also it can have to do with the work being done, or not, the lack of work being done. So most reactions in our lab are going to be with constant pressure because it's really hard for us to change the pressure. In our classroom, we use a lot of open containers. That's like when, in our lab we did last week, we had to find the pressure from using water, basically, which helped us to where we could actually calculate a pressure. Normally we have open containers and it's hard to measure that pressure, so we just use the atmospheric pressure. Therefore, our reaction is doing some work against the atmospheric pressure, and all of our energy is being used as heat. Work is kind of hard to measure for our chemical processes that we do in the lab. So we normally say that delta E and delta H are kind of the same thing. Delta H is the enthalpy of the system. So the enthalpy of the system is the change in heat of a process that occurs at constant external pressure. So the same pressure all around, and we're going to look at the change in the heat. When I think enthalpy, I think heat immediately. When we measure that change in heat, we are measuring enthalpy. And we will do that in a couple labs. It's not the same thing as delta E, but it's harder. It's easier to find than delta E. So it says, number 1, calculate delta E for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and where 1.5 kilojoules of work is done on the system. So I see delta E is going to equal Q plus W, and you just plug and chug 15.6 kilojoules plus 1.4 kilojoules, 17 kilojoules. So the part you have to really look at is the positive and negative with that. So it says that it's an endothermic process. So if I look back in my notes, endothermic means that the surroundings are getting cooler. So endothermic is where the heat is going into the system. So if it's leaving the surroundings, so if it says Q is positive, if the energy is entering from the surroundings, and it says it's endothermic, the surroundings are getting cooler, the heat is coming from the surroundings, so that Q is positive. And it also says that work is done on the system. If I look back again, work is done on the system, our W is also positive. So you just have to look really carefully at your positives and negatives. So let's look at this one. It says calculate the work associated with the expansion of a gas from 46 liters to 64 liters at a constant external pressure of 15 atm. Work is equal to negative P times delta V. Very, very simple, plug and chug. And the last slide, example 3, a balloon is being inflated to its full extent by heating the air inside it. In the final stages of this process, the volume of the balloon changes from a lot of liters to a lot more liters by the addition of that many joules of energy as heat. Assuming that the balloon expands against a constant pressure, calculate delta E for the process. It says to convert between liters, atmospheres, and joules, use 1 liter atmosphere equals 101.3 joules. So delta E equals Q plus W, always. They gave us liters and pressure, so we can use work equals negative P times delta V, get the work. Work is equal to that, and it told us that the heat, the heat was 1.3 times 10 to the 8th joules. Plug and chug. It looks like they said here that heat was positive, meaning the heat went into the system, and it looks like work was negative, meaning that if work is negative, then work is being done by the system on the surroundings. And that's it. So there is physical thermochemistry in a really quick format. There's going to be a whole unit on thermochemistry, so you'll get a lot more of this later on, but this is just like a really quick overview. So, bye.